Good morning. Thank you for attending our presentation on hypothesis testing and automated workflows. First, I would like to extend my gratitude to my co-authors, Jeremy and John, our generous client, and all the INTERA team members that contributed to this presentation. Okay, so I will go forward by stating our motivation for this work, which is to develop tools to answer questions from practitioners, stakeholders, and regulators. Our intent is to have methods to develop what-if questions in an efficient way where we address problems related with groundwater, decision-making, and predictive uncertainty. So we are here to, or in the context of assisting stakeholders avoided unwanted outcomes. And what we are trying to explain is how we can address known unknowns in those problems. And what we are trying to do is to cast them as hypotheses that need to be tested, that can be tested in our problem. And after we test these hypotheses, we continue exploring further the parameter space to see if we are comfortable with the level of risk that we are able to afford for that specific problem. Okay? So as shown during the day, we have this uncertainty analysis workflow based on PyMU, where we follow a series of steps in a very similar way as Andrew showed this morning, or Kevin. We identify the parameters that want to be included in the uncertainty analysis. We define a prior distribution of these parameters. We send that to PEST, where we are able to reduce prior realizations. We go through a process of running our predictive and historical models. In this case, it's a ModFlow6 model, followed by particle tracking. And we use the particle tracking to evaluate the long-term outcome of a contaminant of concern. And we will go and evaluate each of these iterations or we will run this iteratively with PEST. And by the time that we feel comfortable with the number of iterations, we will calculate our predictive uncertainty, which I will explain more detail in the next slide. For this particular problem, we work with 15 parameter groups, around 60,000 parameters, and around 2,000 observations, in a similar setting as shown in the previous presentations. So what we obtain from this is a map of posterior escape probability, which I'm showing here on this side, is the escape probability of particles that define the state of some mine workings. The color reflects the probability of these particles to escape the decision boundary. And as you can see, the probability is rather low at the level of 0.5. I also show an important fault that was parameterized in the model, and we examine further with the hypothesis testing. So this is our initial point for our stage for the analysis that I'm going to present here is this uncertainty analysis. And what we are doing is defining general hypothesis is there might be a set of parameter values that will increase travel distance of these particles that are reasonable, and they will match the observations that we have nearly as well as our original posterior ensemble obtained during the first stage of the uncertainty analysis. So we will then have a rejection criteria based on having unrealistic parameter values or having an unacceptable misfit with the calibration dataset. John and Catherine presented a very nice summary or framework on quantifying predictive uncertainty back in 2020, and that was one part of the framework that helped us to conceptualize all this work. So let's now go in detail into what we did. So I'm summarizing our analysis only with just one particle and a 20 realization ensemble. As I show you here, This is our initial particle, and a probability of 0.5 will result in just one particle escaping this decision boundary. Through the use of automated workflows, we will collect statistics of those particles and store them for analysis. And one of the things that we were analyzing was the distance to the boundary. So if the distance to the boundary is positive, that means the particle escaped the decision area. If it remains negative, there was not a problem with the particle. Okay? So the unwanted outcome is this situation where only just one particle will remain inside, and most of the particles escape our decision boundary. And that's where we are setting our question. Is there a reasonable parameter set that could result in this unwanted outcome? And then we went into the mechanics of forcing our uncertainty workflow into this situation. So we explored different methods to do this, and we codified this into our hypothesis testing by examining the distance that the particles travel from start to end, and establishing an augmenting our objective function by asking the particles to move 10 times more than they move initially. We didn't set as a target simply how the particles to escape the decision boundary, because that might be discontinuous, or forcing to move certain distance. Instead, we just push them a little bit more or what they moved before to see the effect. And we did it just by one order of magnitude. It was enough for our analysis to continue. We had to try other ones. And I will now continue explaining you these steps in more detail. So we have our workflow. Our original workflow is coded in orange, where we have our prior parameters, our observed heads. We obtain our posterior parameters, our posterior heads, and the distance traveled. And then we augment that objective function by having these distance travels multiplied by 10. And that's part of our new target. And then we also have a way to augment our parameterization. And this is the fun part after having all this built, is where we can start to inquire the what-if questions that our client had. First, we work with the original set of parameters. In this original set, we didn't include porosity as a parameter that we will change during the history matching, because we didn't have information to constrain the particle travel time. We proceed with what I'm going to show next is to let porosity move, the porosity parameters move for the unit of interest. That's the one will be presented. But we also, after doing that, we continue pushing the model, trying to crash it against this iceberg of the unwanted outcome. And we increase the K in the main workings area. We increase the K along the fault and in both. And that was the fun part. That's where we can include that. And then after augmenting the workflow, we obtained our augmented posterior parameters, our augmented heads, and our new statistics. And then that's the part where we proceed to examine the effects of these hypotheses. Okay? So let's now look at the results. I'm using violin plots that shows a smooth histogram of the distribution of the data. So here I'm showing all the particles. It's a summary of all the particles from all realizations for each of the iterations after we augmented the workflow. So that's our original posterior, and that's our selected augmented posterior. We decided to stop at iteration 4. And we can see how we stretch the tail of our distribution. And we did it only just by a factor of 10, trying to put the particles by the factor of 10. But this was basically where we obtained. We are not able to push the mean or the median of the distribution of these particles by that factor. Okay? If we examine now the particles in terms of the distance to the boundary, what was what we were caring about at the beginning, we see that we were able to push some of the particles out. You look at here at the mean and the median, they were negative at the beginning. And we were able to push the mean value, thanks to these extreme values, out of the decision boundary. The egress probability was around 0.5, and by iteration 4, it was 0.15, okay? So we continue exploring further our results, and we develop this plot to show the trade-off between distance to the boundary and the error component related to our observations. And as you can see, as we go through the iterations of PEST, or IS, we obtain a distance to the boundary, mean distance to the boundary increases, and we have a moderate increase on our error. And this moderate error increase was moderate compared to other hypotheses that we tested, but there was this trade-off that as we try to push the particles further away, we have this deterioration of our ability to fit performance. But since it was moderate, we went and take a look at our hydrographs. This is an example of our original posterior, and these are all the observations, and we kind of capture the trend of the data in our original posterior analysis, and then we impose our augmented posterior. We have a metric to reject this. It's rather similar, and we were not able to reject at this particular location. The bias is even on up and down. It's a little bit more spread. And we then went and looked into all the targets in a semi-automated way and did the evaluation at all these different locations. And we can see that overall, we were unable to reject these hypotheses in terms to the fit. The deterioration of our ability to fit the observations was not as big as we will imagine to have rejected the hypothesis. Then we went and take a look at the parameters, which is the aspect that was interesting for us. Very interesting. That's the reason why I selected this hypothesis. Here we have the results of the posterior parameters for the unit of interest, for the unit where the mine workers are located. And here I present statistics for the members of the ensemble. So for the median, I'm presenting all the median values from all the realizations, the 25th percentile and the 75th percentile for porosity and specific yield. By looking at this from the original uncertainty analysis, we saw that was this reasonable. We didn't have much more additional information to reject them or to think there will be something wrong. But by the time that we augmented the workflow, we can see how, as the numbers of iterations, as we push the particles out, porosity tend to go down to increase groundwater velocity, to let those particles escape. We did it only by, we did this by a factor of 10. We obtained a probability of 0.15, but we really pushed them to the edge, make them look like unreasonable to us. And at the same time, we have the specific yield increase of remaining under the porosity values. By definition, is the amount of drainable water in a unit, in a volume, in a unit of groundwater media. We could see how a specific yield increased. So we rejected this. We were obtaining unrealistic parameters. And that's how we evaluated this hypothesis. I forgot to mention that for other hypotheses, we were able to reject in terms of our observations. We had bias observations or fit to the observations. And in some other cases, we were not able to reject, but our probability of escape was lower than the original probability of escape. So there were different situations, but that was overall what we obtained. And with these, we show how predictive hypothesis testing is feasible thanks to the efficiency of ensemble methods, because we can codify all these in our automated workflow. It becomes really easy to test different sets of hypotheses about the parameters. And where we are hoping is, as a community, we can focus on energy into defining metrics needed to codify these hypothesis tests and rejection criteria. And that's what I wanted to share with you. And if you have any questions, I'm happy to answer. Thank you.
Guillermo, that was a great talk, well delivered.
Thank
But,
you.
we go to conferences and write papers to show how great everything ended up in the end. I wonder if you'd like to comment on how many times we actually had to run that entire workflow during this process, and share a little bit about the pain and suffering that went into it.
Yeah, that's true. And maybe I went a little bit too quickly when we were defining our metrics, no? And that we had to try different iterations.
Talking about how many times we actually ran the entire process.
Oh, yeah.
History matching and testing the posterior.
50 times. And it was something that we will run overnight during many periods. I remember compared to my null space Monte Carlo that we ran before, I remember it was only six times. But for this, we were able to run it multiple times.
Maybe it's a reoccurring question, but you stopped on iteration 4. Was there any particular reason? Was it just unrealistic parameters where it was going to?
Of the augmented posterior?
Yeah, it was iteration 4.
Well, maybe you were able to see that the statistics were rather similar. We even pushed it up to 10, but we decided just to look at the parameters at that time because we thought the parameters were still reasonable. If you remember, porosity was pushed to the bottom boundary, so we wanted to have some spread of the parameters instead of collapsing all porosity to a very low value and unrealistic value. So that was our criteria. We are here working in terms of uncertainty, not in terms of the history match itself. It's just to consider different outcomes and have an evaluation of the uncertainty of the problem. So we didn't tend to do that many, but we try when we were exploring different metrics on how to move the particles away.
And I hope I understood this correctly, but the assessment was done on the values of the parameters, but implied in the methodology and the multi-Gaussian distributions on which variability was based, was there any assessment of the shapes of the heterogeneity that arose, or that perhaps could suggest other than multi-Gaussian distributions that could have moved those particles further but weren't included in the analysis because of the use of, you're combining a set of realizations, and it'll be a linear combination of those which will still be multi-Gaussian. Was there an ability for different shapes reflecting underlying structure that could cause unwanted surprises?
We didn't chase them in that level of detail. We just chased them in terms of the aggregated statistics. That's something that we could explore further. That was kind of what we did. But it's that was for what we were obtaining. That's where we decided to stop. But certainly those things are things that can be implemented in following iterations. We tried to summarize all the members of the ensemble using summary statistics, but we could come up with additional metrics to explore spatial patterns that could have a hint of maybe some structure modification or process that we are missing. But thank you.
I think hypothesis testing is the way to go, so I think that was great. Yep.
Thank you. Thank you. Thank you.